In this video, we'll be looking at exponential modeling, which means applying the concepts of exponential growth and decay to something like the population growth in a city, or maybe investment growth from interest in a savings account. So here we have what is called the exponential population model. So for the three variables we have listed here, P sub 0, sometimes called P naught, this is the initial population. So if there was a starting population in a city before you start saying years are going by or months are going by, whatever the case may be, this would be the starting amount in the city. R needs to be a decimal number. So they may say something like 20% growth. You'll need to remember how to change that 20% to a decimal, and then make sure you add that number to 1, because multiplying by 1 keeps the population where it is. Having a 20% growth means 1 plus 0.2, so 1.2. And then T is how much time is going by, usually in years, but there could be cases where they might use a different unit, like months or days or weeks, etc. So T is just going to be how many units of time have gone by. For the R value, you will notice that if R is a positive number, so if they say increasing by 20%, that's why we were adding 0.2. But if it had been decreasing by 20%, then that means R should be a negative number. So this would be a decay function. And then we'd be doing 1 plus negative 0.2, which is 0.8 for your base. If you are given the population model with all the numbers filled in, and then you are asked to find the rate of growth or decay, that would be the R value, what you'll want to do is subtract 1 from the base of the exponent. So if you see something like 1.3 to a power, then subtract 1 from that, and then change that number to a percent by moving the decimal space twice. As a reminder, if you're trying to change between decimal and percent form, remember you're just moving the decimal space 2 times. So if you're going from percent to decimal form, you move it to the left, and vice versa. If you're going from the decimal mode and you're trying to change it back to a percent, you would move that decimal space 2 units to the right to get back to 73. So here are some examples where we will determine if these are exponential growth or decay, and we will find the constant percentage rate of growth or decay. So to find the rate, we're going to take the base of your exponent, and we're just going to subtract 1 from that. So in this case, we get 0.13. Now, since this is a positive number, I'm going to say that this is a growth function, exponential growth. And then we also have to remember to change this to a percent. So if I move the decimal space twice, we would say 13%. Here's another example. We're going to take the base of the exponent, so 0.92. If we subtract 1, we get negative 0.08. So since this is a negative number, we're going to say that this is an exponential decay function. And then again, to get the percent, we just need to take the decimal and move it twice. So this would be a decay by 8%. Notice I'm not calling it negative 8% now. I am only using the positive number. The fact that it was negative is why I said decay, but I don't need to make this negative. And then an example like this sometimes tricks people up, but it's the same rule. So we are taking the base and subtracting 1. Since this is a positive number, I do have exponential growth. And to find the decimal, this counts as 1.0. We're going to move the decimal space twice, so this is 100% growth. So when something doubles, we say it has increased by 100%, and that's what this population model represents. For some of the tricky complications on these questions, if you ever see the term half-life mentioned, half-life means an amount of time for the amount of something to cut in half. So it means that your 1 plus r part, the base of your exponential model, is 1/2. That's counting the 1 plus r already being added together. If you see the term doubling, if they say a population is doubling every certain amount of time, then that means again that the base of your exponential, the 1 plus r part, is just a 2. They've already taken into account the 1 plus r part. Sometimes they will say that the growth or decay doesn't happen every year. Maybe it happens every 3 years. So in this case, I've used the variable n to represent whatever the number of days, weeks, or months it takes is. Then your exponent will go from just being an x or a t, depending on the variable you're using, to being that variable divided by n. So for example, if they say the population doubles every 3 years, I didn't give an initial population, so I just used the variable p naught here. Then doubling means that your base of the exponential is 2. And since they say it's happening every 3 years, not happening every year, I'm just taking my exponent of t, and I'm doing t over 3. If it was every 4 years, I would have done t over 4. If it happened every 5 years, I would have done t over 5. So those are just some of the tricky situations that happen on these. So now we're going to work backwards. What if you were given some of the values and they ask you to write the exponential model yourself? So in that case, we need to remember that our population model, it's going to be the initial amount or the initial value, in this case 29. And then our base is supposed to be 1 plus r. Since this is increasing, then I know that this is going to be a positive r value. So I need to do 1 plus, and then don't forget to change this to a decimal. So 1 plus 0.35 to the t. Now, we don't like leaving our answer with the 1 plus 0.35. I would rather have you guys just go ahead and actually combine those numbers. So 1 plus 0.35 is 1.35. So that's our population model, initial value, and base to a power. Don't forget that if it is a decreasing by a certain amount, then you're actually going to be adding a negative number, or you can think of it as subtracting. It's the same thing either way. So if this had been decreasing, I would have done 1 minus 0.35 instead. So now to actually solve exponential growth or decay model questions, your first step would be to write the exponential function using the given initial population and the rate of growth or decay, just like we did on the last example. And then your second step will be to use a graphing tool to graph the function. My advice is to use the desmos.com/calculator. That's a very good one, but you could also use a physical graphing calculator if you have one as well. But one important comment is when you're typing in your exponential model, make sure you use the exponent for x instead of using a t, or it will not draw the line correctly. So now there are two types of questions they'll give you once you have your exponential growth or decay model written out. The first type of question, they'll give you a target year and then ask you what the population is then. For example, they may say, here's your model, what will the population be in 30 years? So then you would find x equals 30 on the graph, and then the y coordinate at that point will be your answer. That'll be the population 30 years later. The other type of question is they may give you a target population and say, when will that happen? So now they're giving you the y and asking you for the x. So to answer these questions, you're actually going to enter a separate equation into the graphing tool. For example, if the target population was 1,000, you would write y equals 1,000 for a second equation on the graphing tool. And then what you're going to look for is where your two graphs intersect. So find the point of intersection between them and click on that. And the x value where those lines meet, that will be the answer to your question. That'll be how much longer it takes for those two conditions to overlap. So for our first example, we have a population model given for how many students are at Hogwarts at a given year. And do note that this x value is going to be measuring the number of years since 1950. So if we had x equals 5, that would mean 1955. So make sure you add your x value back to the starting number. So they ask us how many students will attend in 1990. We're going to draw the graph for this population model right here. And then that means we're going to be looking at an x value of 40 because this is 40 years from the starting year. So here is Desmos graphing calculator. You can see I've typed in the population model that we were given, y equals 500 times 1.02 to the x. And I don't see anything on the graph right now, but that's because these numbers are so big, I just need to zoom out a lot to find where the function actually exists. Now we're looking for what happens when x is equal to 40. And so depending on how far you've zoomed out, I see that x equals 40 is going to be this fourth tick mark here. So if I'm clicking on the dot and then scrolling it along, as soon as I hit x equals 40, that y value will be my target answer, so the 1,104. So we've identified how many students were there in 1990. Now we're going to look at how many they should anticipate being at the school in the year 2025. Again, my model starts from the year 1950. This is the beginning value. So from 2025 to 1950 is going to be 75 years. So we're going to be looking at what happens when x equals 75 in this case. So going back to my graph, I need to find the height when x equals 75 now. So I need to continue to scroll up on here. And then here we can see that when x is equal to 75, the height is 2,208 by rounding to the nearest whole number. So 2,208 would be the population in 2025. So for questions where they give you a specific year or a number of years passing by, you have the x value, you're going to identify the y value for that coordinate. So now we'll look at the other type of population model question where they have given us the equation again to model the population of some object. In this case, it's the number of centaurs in the Forbidden Forest. And then they want to know when will that population hit 600. So for this style of question, you're going to have two equations drawn into Desmos. You're going to have y equals, and you'll have to type all of this in. You can literally use the E key when you're typing in, and it will do that value of 2.718 raised to a power. And then your second equation is going to be y equals 600 for the target population here. Again, I'll reiterate the importance of using the variable x instead of t when you're graphing this into Desmos, because Desmos is reading this as an x and a y axis, not as t for the horizontal scale. So you do need to change that variable for the graph to show up. Now, right now, I don't see both my red and my blue lines. So again, it will often be helpful for you to zoom out a fair bit until you see the intersection. And then once you identify that location, zoom back in to get a close, precise answer of where they're intersecting. So now when I click on the dot of intersection, it shows me that the x value, which is my answer this time, is going to be the 24.5, and that has my y value of being exactly 600. So they may ask you to round to the nearest whole number, 10th, 100th, whatever. For this one, I'm just going to round to the nearest 10th and say 24.5 years is when this will happen. So now for writing my answer, again, I'm using the variable t to represent that this is a time, and I said 24.5, I rounded to the nearest 10th. But don't forget the last trick or complication here, that's the number of years after 1950. So if we're trying to say what year this population occurs at, we need to remember to add that to the starting value. So in this case, we actually say that the population of 600 will occur in the year 1974.5. So that's all for this lesson. I hope that was useful. If the video helped you, please make sure to hit like, subscribe, or comment.